All right, let's jump right in. Welcome everyone to today's Explainer. Today we're unpacking something absolutely massive, the complete physical and digital transformation of Earth's orbit. For decades, we've thought of space as this sparse, empty void, a place mostly reserved for quiet scientific exploration. Well, you can toss that mental model right out the window. Today, near-Earth space is rapidly turning into a highly congested, multi-trillion-dollar industrial zone. And it's happening incredibly fast. Here is our roadmap for today's deep dive. We'll start with the orbital architecture evolution. Then we'll look at the rise of the space supercomputer. Third, we'll examine China's mega constellation market challenge. And finally, we'll tackle the Illumina pollution threat.
So let's get right into part one, the orbital architecture evolution.
To really grasp what's happening up there, we have to kind of break our old assumptions. The traditional way we think of a satellite is basically as a big, passive mirror. A signal goes up and it bounces right back down to a ground station that has to be geographically close by. But the modern new space architecture, it's completely different. Spearheaded by networks like Starlink's V3, we're not looking at an optical laser mesh. Instead of relying on that terrestrial bottleneck, these new satellites use high-speed space lasers to dynamically route data directly to each other while still in orbit. It's essentially a giant, flying fiber optic network, and this completely slashes latency, especially over vast oceans where you literally cannot build ground stations.
4 terabits per second. Just let that number sink in for a second. That is the staggering combined radio frequency and laser backhaul capacity of a single Starlink V3 satellite. By outfitting each spacecraft with 3 independent space lasers, each operating at up to 200 gigabits per second, this new architecture sidesteps ground congestion entirely. It maximizes global coverage in a way those old, monolithic satellites could never even dream of.
Now, when you multiply that kind of power across the current orbital landscape, this scale is just wild. Looking at early 2026 data, SpaceX's Starlink has established a near monopoly in orbital presence. We're talking about 10,260 active satellites. That is over 66% of all operational payloads currently circling the Earth. With the V3 architecture delivering a massive 1 terabit per second of downlink capacity per satellite and cruising at exceptionally low altitudes, they're hitting latencies of just 20 to 40 milliseconds. This right here is the baseline of our modern orbital environment, standardized, mass-produced commercial nodes, all operating in perfectly synchronized networks.
But hey, this evolution isn't just about bouncing internet signals faster. That brings us to section 2. Enter the space supercomputer.
So what exactly is orbital supercomputing? Simply put, it's the practice of processing massive amounts of raw data directly on board the satellite itself, right at the very edge of the network, using spaceborne AI. So instead of the spacecraft acting as a passive data collector that just blindly beams everything back to Earth for us to analyze, the satellite actually analyzes the data itself.
Why is that such a game changer? Well, historically, up to 90%, 90%, of the raw data generated in space is discarded, overwritten, or just plain lost. Why? Because the radio frequency downlink bandwidth is super limited, and ground stations aren't exactly everywhere. The old system was incredibly inefficient. You had terabytes of brilliant data completely bottlenecked by the tiny digital pipe connecting space to Earth.
So, enter orbital AI. A great example is China's 3-body computing constellation, which achieved a 99% accuracy rate in real-time orbital classification. By running massive 8 billion parameter AI models natively onboard their satellites, they autonomously classified highly transient, unpredictable gamma-ray bursts. The AI instantly throws out all the useless background noise and only transmits the critical scientific conclusions back to Earth. It completely solves that downlink bottleneck we were just talking about.
And there's actually a surprising secondary benefit to all this, which is super fascinating. Space acts as the ultimate heat sink. Think about it. Terrestrial AI data centers down here on Earth are incredibly power hungry. They generate massive amounts of heat and are projected to consume over 1,000 terawatt hours of electricity annually by 2026. But in orbit, satellites have continuous unhindered access to solar power, and they can passively radiate their intense thermal loads directly into the infinite freezing vacuum of space. You get to completely bypass all that massive, costly cooling infrastructure we need down here.
All right, shifting gears a bit, let's move into section 3, China's mega constellation market challenge. You see, the current near monopoly held by Western commercial operators hasn't gone unnoticed.
It's triggered a highly structured, state-backed architectural response from China. They clearly view sovereign orbital infrastructure as an absolute pillar of national security and economic independence. To prevent Western monopolization of these vital orbital slots, they're deploying a really interesting dual-pronged challenge. On one hand, you have the Guowang project targeting around 13,000 satellites operated by a central state-owned enterprise. This is their strategic sovereign network. And on the other hand, there's the Qianfan constellation, with a staggering 15,000 satellites planned. This one is a commercial-first system explicitly designed to capture international export markets and go toe-to-toe with global competitors. To actually meet these massive deployment mandates, China has fundamentally restructured its aerospace sector. They've completely abandoned the old-school model of bespoke, small-batch engineering. Instead, we're now looking at highly automated assembly line production, with specific facilities targeting the production of over 400 satellite platforms every single year. Producing spacecraft at that kind of volume, it's an incredible industrial pivot.
The explicit goal here is clear: secure physical low Earth orbit, or LEO, slots, along with finite spectrum allocations. To pull this off, they're planning a combined total of nearly 28,000 broadband satellites by the mid-2030s. But there is a catch. They face a persistent bottleneck: reusable, heavy-lift launch vehicles. Because to launch that many satellites economically, you absolutely need rockets that can land and be rapidly reused, a capability that is still actively undergoing testing in their commercial sector.
Which brings us to our fourth, and honestly, perhaps most sobering section of today's explainer, the Illumina pollution threat.
Space might seem infinite, but low Earth orbit actually has a finite carrying capacity. It's a physical space. And aerospace engineers are warning that if we exceed the mathematical limit of what can safely coexist up there, we risk triggering the Kessler syndrome. That's a terrifying cascade of high-velocity collisions that generates unmanageable clouds of shrapnel. Current analytical models suggest that this hard practical limit hovers somewhere around 100,000 active satellites. So, to prevent this exact debris cascade from happening, the industry uses a very specific disposal mechanism. When a satellite reaches the end of its typical 5-year operational cycle, it's intentionally deorbited. It undergoes atmospheric re-entry, where the intense friction and heat cause thermal vaporization. Basically, the satellite burns up. For a long time, we all thought of this as a super clean solution, right? No debris left floating in space. But this creates what we can call the re-entry paradox, which leads us right to step 4, Illumina particle formation.
Because here's the core of the problem. Vaporization isn't some magical vanishing act. It's simply a phase change. 100% of that massive satellite's vaporized mass turns into highly reactive metallic aerosols, and those microscopic particles are deposited directly into the Earth's upper atmosphere.
And the atmospheric chemistry here is pretty stark. Advanced molecular dynamics simulations confirm that this thermal ablation widespreadly forms highly reactive aluminum oxides, or alumina. Because we're rapidly moving toward a reality where thousands of these massive satellites are continuously vaporized every single year just to replace old hardware, we are threatening to dump thousands of metric tons of alumina right into our fragile stratosphere. Environmental scientists are sounding the alarm that this threatens to severely deplete the ozone layer and permanently alter Earth's global atmospheric albedo, meaning it could change how much sunlight our planet naturally reflects. And right now, this exists as a largely unregulated environmental risk.
So this leaves us with a pretty massive question to chew on. As we aggressively build out this incredible multi-trillion-dollar digital nervous system in orbit, bringing high-speed broadband to the entire globe and putting actual supercomputers into the vacuum of space, are we simply trading the problem of space debris for a permanently altered atmosphere? The technological triumphs we've covered today are genuinely astounding, no doubt about it. But managing the physical and environmental realities of this brand new orbital architecture, that's going to be the true defining challenge of the next decade. Thank you so much for learning with me today, and I really hope this leaves you eager to explore the future of global space governance. Catch you next time.